So I'm going to record this thing. What we are going to do now is we're going to obtain the differential equations for the cart pole system, and after that we're going to simplify them to fit the format of linear system. So we're going to consider the system in a neighborhood of an unstable equilibrium. We are going to consider a certain linearization point where the whole system will be simplified a lot. Okay, so the first thing that we're going to do is we're going to simply write down the kinetic potential energy, and we are going to subtract them, obtaining the Lagrangian. Hi, Nev and John.
Good evening.
Fatima. Hello. Fatima, are you here for the first time, or you were?
Yes, this is my first time.
Okay, awesome. So, what course are you at? So, what do you study? Computer sciences, mathematics, what, mechanics?
Aerospace engineering.
Excuse me?
Aerospace.
Aerospace. Okay, nice to meet you. My name is Ilya. I'm a PhD student at Moscow Institute of Physics and Technology, and we're going to have a course here. We're having basically a course on control in application to humanoid robots, to robotic football, to be more specific. So we're talking about control, and we have discussions on anything that is related to computer vision, humanoid robots, and so on. So you can join us if you would like this. Now, the topic of our discussion is the system, the dynamical system that consists of a cart and a pole that is attached to the cart. So we're going to do some differential equations, theoretical mechanics. And what year do you study?
This is my first semester and my last year, senior student. I'm a senior student.
Okay. Okay. So it would be cool if you could ask questions if something is not clear, and you can ask questions about robotics, competitions in robotics. I'm just saying that Khalifa University is opening a team in robotic football, so that's why I'm here, basically. I don't know if you are into this topic, if you have seen the news about this team being opened in KU, but anyways, so there will be robotic football, and now we are learning towards that. We are learning control. Probably if you're doing aerospace, you already know a lot of that stuff that I'm going to cover, but anyways. So last time we were talking about Euler-Lagrange equations, and we have applied them to obtain the differential equation of motion for an inverted pendulum, for regular pendulum, and for another system that was a pendulum that was attached to a vertical spring. So it was capable of moving and oscillating. And now we're going to consider this system. Is it clear what's going on? Just asking to make sure.
Yes,
Okay.
it's clear.
Okay. Okay, so the length here is L, and I'm going to first write down the kinetic energy of this system. It consists of two parts. The first part is the kinetic energy of the cart, and it's m over 2 x dot square. X dot just the velocity. And the second part is a bit more tricky. So there is a pole over here and the second mass that is moving with some velocity, but there are two components to it, vertical and horizontal. So I'm going to I'll write it down like this. The vertical component doesn't depend on the horizontal motion, right? So it would be the vertical component. Let us project that. So the velocity is pointed somewhere there, and the vertical component will be theta dot square L square. This is the squared linear velocity of this mass times the sine of this angle, sine theta, sine square theta. That is the vertical velocity, the square of the vertical component. And now we are interested in the horizontal motion of the pole. So it would have the same part as here. I mean, theta dot times L times, now this time cosine theta. Cosine theta. And now comes the tricky part. So we have to, Hi Muhammad, we have to consider both the vertical part, the horizontal velocity of of this mass that comes from the rotary motion and from the linear motion. Okay, so they will have a different sign because if theta dot is positive, the mass is moving counterclockwise, and here it's to the left. And if x dot is positive, the mass is moving in the opposite direction. So here we are going to have minus x dot, and it would be squared like this. I'm going to close.
Sorry, could you repeat that?
Yeah. So let us. I'm just going to draw it over here to declutter slightly. So let's assume that x dot is positive. Strictly, the cart is moving to the right, and and then let us assume that theta dot is strictly negative. So if theta dot is strictly negative, it means that the pole is rotating counterclockwise. So the cart is moving to the right, and relative to the cart, the pole, the mass, is moving to the left. So it's like me moving to in that direction, and simultaneously counteracting that by rotating the marker like this. You get the point? So part of the velocities are compensated. They're canceled out.
Wouldn't we consider anti-clockwise, like moving anti-clockwise as positive usually?
Oh, sorry. Exactly. Yes, you're right. Thanks. The argument is valid. I'm just mistaken slightly. Sorry for that. You're right. Okay, so counterclockwise, positive, and this one is positive as well, and they're counteracting each other. This is why we have minus here. Yes.
Okay. Yeah. Okay. So we're subtracting the horizontal component of the rotational motion from the movement. So the rotational motion it's moving in the opposite direction to like the way the mass is moving.
Yes, so if both these velocities are positive, they are counteracting each other, and we can check we can perform a sanity check. So if theta dot is 0 and the pole is not going anywhere, the angle is just stationary, the whole horizontal component of the velocity is just stored in x dot. Otherwise, if x dot is 0 and x of the cart is not changing, the whole horizontal motion of the pendulum is just the horizontal part of the rotary motion. So it will be theta dot square, L square, cosine square.
Okay, that makes sense. Yeah.
Great. So let us reorder that a bit. But, well, yeah, basically going to open the braces, and it would be simpler. So I'm going to group this guy and this guy over here. Here we have theta dot square L square times sine, and the same thing times cosine. So we're going to have m over 2. And here we have theta dot square L square. And the last part is this one. It will be minus m theta dot x dot cosine theta. Awesome. So there is the kinetic energy. There are surprisingly many of us today. Who is here for the first time? Raise your hands. Or write anything in the chat. I don't know. Okay. Okay. Mm-hmm. Okay. So I think I will have to say a couple of introductory words, I guess, in the end of the session, if you don't mind, just to familiarize all of you with what we're doing with the league, what is actually robotic football, what's the point, and what's going on. Okay, so I'm planning to do it in the end of the session, just not to break up the discussion about this thing. But if you are very curious, you can ask even right now, like, why should we care? That's a nice question. Why should we care about these pendulums if we are working with robots? I hope you see the writing. Yeah, seems like it's fine. So we're done with the kinetic energy. With the potential, by the way, it's much, much simpler. I can write it over here. The potential energy is m times g times L times cosine theta. It's just the elevation of the mass is L cosine theta, and we're multiplying that by the force that we're counteracting if we are uplifting the mass. So that's pretty straightforward. So the Lagrangian is equal to the kinetic energy minus the potential energy. And after that, we'll have to do the second part, which is to differentiate we will have to obtain two equations of motion in the following form. This is the force that we exert upon the pendulum. We have lost one user, seems like. And I know that Fatima is from the senior year, Mohammed and Guo Kuai. Sorry if I mispronounced that. So what year do you study at? Senior year also. Okay, got it. So I'm assuming that you're familiar with differential equations, right? But still, if anything is missing, please let me know. So I'm going to move second whiteboard over here. Yeah, so I'm going to rewrite the most important parts, and then I'm going to move this whiteboard over here. It will be fine. So the Lagrangian is equal to m plus m x dot square over 2 plus m over 2 theta dot square L square minus m theta dot x dot cosine theta minus m GL cosine theta. Awesome. So yeah. And let us obtain the differential equations of motion. First, I'm going to differentiate by x dot, which is one of the generalized coordinates. Oops, qi and q and I goes from 1 to 2 basically. So it's It's here. Because our system has 2 degrees of freedom. L is the Lagrangian. Lagrangian, let me show the previous, oh, sorry. The previous whiteboard. Lagrangian is a special function that is equal to the subtraction of the kinetic and potential energy. There is a subtopic in theoretical mechanics that is that goes by the name of Lagrangian formalism. And we are using that Lagrangian formalism to obtain the equation of motion, the equations of motion of certain systems. So we have started with an inverted pendulum, and we have used that formalism to get the same equations that we can get using our intuition. And now we are considering a more complex system. The essence of the Lagrangian formalism is that at first we construct the formula for the kinetic energy, then for potential energy, then we subtract potential from the kinetic. It gives us the Lagrangian, this function L. And if we plug in this Lagrangian into these equations, we will get the differential equations of motion. We have had, we have basically here 2 degrees of freedom. This is 1 degree of freedom. This is another degree of freedom. So we're going to have 2 different differential equations, and one will correspond to Q1 and another to Q2. Q1 will be X, Q2 will be theta. The examples and more detailed explanation is on the YouTube. I have shared that in the chat, so you can reach that if you would like to, and you can check it. Okay, so thank you for the question. Please ask any questions if there are some. So let us obtain the equations of motion using the Euler-Lagrange equations. I'm going to plug this Lagrangian, this whole function, into this thing for Q1 and another thing with Q2. So dl by dx dot is equal to m plus m x dot minus m theta dot cosine theta. The first term, the square over here is gives us 2 that is cancelled with the denominator, and we're left with this constant times the first order of x dot. The second term is not dependent on x dot. The third term is dependent linearly, so we end up with m theta dot cosine theta, and the last term is not dependent on x dot. Cool. Now let us calculate the time derivative of dl by dx dot. Is it clear what is going on? Please tell me your honest feedback. So do we have to run slower or faster, or is it fine? Tell me. Okay, awesome.
Clear so far.
Okay. But please, if something is not clear, please tell me about that. So I'm going to differentiate this thing by time. And in the first term over here, the masses, they're just constants. So the only thing that will happen is we're going to get x double dot instead of x dot. X dot is a time derivative of x, and x double dot is a time derivative of x dot, x double dot. Now we will have to differentiate these two parts. So m is just a constant. The first term will be with theta dot being differentiated, and it will give us theta double dot times cosine theta. And the last term, the second that will come from here, will be the following. It will be plus m theta dot sine theta, because cosine differentiation and also
the chain rule there?
yes, and also it will give us theta dot. So theta dot will be squared over here.
So so we consider theta dot as the first function and like cos theta as the okay. And we just the product rule and the chain rule together.
Yeah, I think so. So we have two things that are dependent on time, and there we're differentiating. The first is pretty straightforward, and the second we're doing the following. M theta dot comes from here, then we're differentiating cosine. It will give us minus sine. Minus goes here, sine goes here, times the time derivative of what's inside the sine. It's theta, so d by dt of theta, it's theta dot, and it ends up in the same spot where the first theta dot belongs, so it's theta dot squared. Okay, this is the first term of the first equation. And the second term of the first equation is dl by dx. And what is that? What is that? It's 0. Why is it 0?
Because there's no variable
yes,
with
and basically it means that the flow of the energy, these differential equations are responsible for the flow of the energy. The flow of the energy doesn't depend on the linear position of the cart, which makes a lot of sense. We can move the cart 10 units to the right, and nothing will change with the energy. However, if we, say, move the pendulum counterclockwise 10 radians, the energy will change. That's why this guy is equal to 0. So,
but if we move the mass by like a certain distance, wouldn't we be doing work on it?
I mean, if we move, well, let us consider three different states. I have formulated that not clear enough. So let us consider three different states of this system. One state is should be horizontal, like this. One state is with the x in 0 and theta in 1 radian. The second state is in x 0 and theta 2 radians. And the third state is with x equal to 10 and theta 1 radian. And what I'm saying is that the energy of the system is not dependent on the value of x on these coordinates. So we can move, I mean, virtually move this card around. We can change the units, and if everything in the state vector is the same, and the only thing that is changed is x, then the energy will stay intact. So the state vector here is x dot theta dot. If we are going to keep these elements intact, and if we are going to change x, we're like freezing the time and moving in freeze time. It's not the work of the controller, so we are moving it by as the designers of the system. If we are changing the x, we don't change the energy. However, if we say increase the velocity, the energy will change. If we'll change the angle, the potential energy will change. And if we change the, well, you get the idea. That's the difference. So x is the only unique coordinate and the only unique part of the state vector upon which the energy does not depend. And here also we should say that x and x dot, we're considering them to be fairly independent. I mean, one, of course, is the derivative of another, but if we're differentiating by one, we are not differentiating by another. And now let us assemble from two parts, this one and this one, the first differential equation. So it will be the first differential equation of motion, m plus small m x double dot minus m theta double dot cosine theta plus m theta dot square sine theta. And it is equal, well, it would be equal to 0 if we are not acting upon the mass. Let us not act upon it for now. This is the first equation of motion. Awesome. So it's fairly complicated, and while linearizing the system, we will simplify this equation of motion a lot. But for now, let's leave it like this. And let us then derive the second equation of motion. By d theta dot, it will be nothing. Here it will be m L square theta dot. And also we're going to have this term. So it's minus m x dot cosine theta. Nice. Now let us take the time derivative of that. And it will be m L square theta double dot minus, here's the same logic really. So it's minus m x double dot cosine theta plus m x dot theta dot, that comes from the chain rule, sine theta. And the partial derivative of the Lagrangian by theta. Hope you can see the writing. Yes, you can. So this derivative will be equal to nothing here. It will be minus. So I'm going to move the cosine out of the braces here. I will factor out cosine theta because it's pretty unique over there. So it's m theta dot x dot plus m times g times L. And well, I'm going to write this with a different color just to make it clear. Ah, there was a marker somewhere. Hold on. Where are they going? Ah, it's here. Okay. So this thing, it's basically with the sign, okay? It's minus m theta dot x dot plus g times L cosine theta. And this is exactly what I'm doing over here. So this thing is not dependent on theta, and I'm treating it like a constant. The only thing that is dependent on theta is the cosine, and being differentiated, it gives minus sign, which leaves us with plus this thing times sine theta. And I'm going to erase this part over here. Okay. So let's write down the second equation of motion. It's this part minus this part. D by dt of this thing, of course. So m L square theta double dot minus m x double dot cosine theta plus m x dot theta dot sine theta minus this thing. It's minus m theta dot. It's pretty tedious, but we'll have to do it anyway. X dot sine theta. By the way, it's being cancelled, which is nice. So instead of the cancelled thing, there's a second term over here, which is minus m g l sine theta is equal to 0. What would you say? Is it clear so far?
Yes.
Okay. By the way, did someone manage to contact Ahmad or Bushra or Dr. Hamad? You know who they are? Dr. Hamad Karki, maybe.
Contact them about the physical classes.
About physical classes?
What are you asking about? Like contact them about what?
I'm asking if you know who they are and if you know how to find them out, because there will be sessions that will be held in person in KU with physical robots, because I'm in Moscow and the other PhD student is in KU, and he's going to tell you stuff about running the robots physical and participating in the competitions, changing servo motors, all that stuff. So it's a bit.
I think Bushra is trying to organize the physical meetings in the group chat right now. She's asking for times people are free, and she's gonna set up something.
Okay. Could I ask you to add the rest of the people over here in the proper chat in WhatsApp? So guys, try to organize yourself somehow, because I'm not even present physically. So try to organize yourself and try to find out what's the team about, what's going on. Okay. So is it possible? You know each
Send
other.
the group link in the chat of the Zoom meeting in case
Yes.
anybody is not already there.
Yeah. Yes, please. Okay. And if it is not clear, why do we even need this? We need this because CartPole is a very, very, very simplified version of a humanoid robot. And if we will manage to create a control algorithm that will be capable of keeping the CartPole near the equilibrium under some disturbances, we will be happy about the control of much more complicated systems, such as the humanoid robot, really. So thank you for sharing the chat. So I'm going to, excuse me, I'm going to.
If we look at the equation of, could we go back to the equation for a second?
The last ones.
Yeah.
Sure.
Do the dimensions match up?
Where exactly?
In the final equation,
This one.
Yeah.
Okay, so let's check that. Kilograms times meters, meters squared, and it's seconds in the power of -2, because it's radians per second square, minus kilograms times meters times seconds -2. Cosine is just 1. How come? Okay. How did we end up with this? It comes from here, and this guy comes from here. Here it is. From where exactly? Okay, so let's double check. The Lagrangian energy Okay, so let's check this part as well. Kilograms, it's seconds minus -2 because of these two derivatives, and also meters. And here meters times something doesn't match here, does it? Okay, so let's check that together. Kinetic energy. This is pretty straightforward. This is the second part. It's the velocity squared. So far, so good. Here we are reordering stuff. This is the first term, the square term. L is missing. Here L is missing.
Yeah.
Yes. Thank you. Thank you. We would have a lot of problems programming this thing because of this mistake. Awesome. So it will be another L over here in the Lagrangian. It's just a constant, so we'll move it fast enough. But thank you very much for driving my attention towards this. There is L over here. There is L over here. Now it will match because yeah, it's like this. We are factoring L out, and it's meters over second square, and here again meters over second square, which is awesome. So by dx dot L okay, just another L over here and L over here. Fine. Here, what's going on? Here we're going to have by theta dot, so it will be here, and here we are going to have it as well. So L here and L here, and here. Yeah. So here it will be really differentiating this thing. So it will be plus M L theta dot x dot plus g times sin theta. Great. And here, finally, minus ML x double dot. Here, M L x dot theta dot sin theta. And here will be ML theta. Okay, I'm going to just rewrite it. ML theta dot x dot plus G sine theta. So this thing over here will cancel with one of the parts of the last term, with this one, because it's m L x dot theta dot sine theta. And what we will get as a result is the following. I'm so grateful for you noticing a mistake over here. Yeah, okay, so the equation, since there is nothing acting upon this system, the second differential equation is the following. M L square theta double dot minus M L x square cosine theta minus M L G sine theta is equal to 0. So this is the first equation of motion. And this is the second equation of motion. And I'm saying that the motion of this cart pole system is guided by these two differential equations. Last time I have promised that we will do some programming, but unfortunately we didn't manage to do that. So I think that the next time our session will be longer and we'll be able to finally simulate something. I hope that all of you will join us, and if there are any questions, you can ask them here or in the chat or whatever. So I'm very much pro that. And also join the chat, check the online sessions, check our robots. Questions, proposals, anything?
Now,
Comments?
you've got these two equations, like they describe the system essentially.
Yes, the motion of the system. Yes, exactly.
So, like, assuming we have like, okay, a more like a realistic example, say we have like, so if we know certain aspects of the system, we can use that to calculate other aspects of the system using these two equations, just like the regular laws of motion, basically. So is that what we have these equations for, or is there like another purpose to them? Like in terms of robotics, how do we?
I get the question. So the main purpose of obtaining these equations is for us to be able to simulate the behavior of the system, because later on we're going to introduce the control into one of these equations, in this one exactly, on the right. And what will happen is that we are going to try to guide our system to a certain state. We're basically interested in guiding the dynamical systems into certain states. If I'm a robot and I'm trying to stabilize myself, I'm exerting certain range with my feet and with my back and with all the other parts. And I'm trying to stabilize myself into an upright position. If I'm after that going to approach the ball and kick it. So as control engineers, we're interested in generating proper control to drive the system to a certain state. And in order for us to do that, we have to be able to predict the behavior of the system given a certain control.
Okay, so we change we apply certain forces, or like we change the system and essentially try to set certain values for theta, or like the velocity.
Yeah, I get the question. So let's say, for example, that our system is in this state, and we want to drive this system into this state. So over here. So for us as humans, it's pretty intuitive to pull the block to the right. We can only exert forces on the block, on the cart. The pole is freely spinning. We have to balance it, like I'm doing with this thing. You get it? So yeah, for us as humans, it's pretty intuitive to rapidly move the block to the right, and then it will stabilize the cart, it will stabilize the pole, and it itself will be over here, positioned over here. And what is basically happening is we're applying the force. In terms of the control systems, it is U sub K. By U, we usually denote the control. And here, the control is one-dimensional, since we can drag and pull this cart to the right and to the left with force. So our controller is saying, say, 5 newtons. And for a period of time, 5 newtons are exerted by the motors onto this cart. And the behavior of the system is described by these two differential equations that we have tried for a period of time to derive. And after that, we will be able to use them to predict essentially the behavior of the system in order for us to guide it to a certain state, to a desired state.
Okay. I think it makes more sense. So we're basically trying to find these equations so that we can manipulate the system into certain states that we want.
Yes,
Okay.
exactly.
Now,
Thank you. That made a lot of sense. Yeah, it was a really great explanation.
Thank you for coming, all of you. Basically, there are 2 of you left, but we see each other. We have seen each other several times already. Thank you for coming, and hope to see you next time again. And please check the facility, check the physical robots. I bet you will like them because they're
Yeah,
in KU.
we'll definitely go check them out. Thank you for having the lesson. Have a nice day.
thank you
Yeah,
so much for
and you.
taking the time to answer everything. And I'm really, really appreciative. Thank you so much. Thank you.
Thanks.
Thank you.
See you.
Bye.
Could I ask also, just like,
Yeah, sure,
what
of course.
what kind of libraries would you use for Python, just like to solve these and like uh, to solve those differential equations? What libraries would you use if?
The main tool basically is NumPy. So
Okay.
also I have to say that by now the majority of the things that we are doing with the dynamical systems fall into 2 main categories. The one is the sort of production that is being written in C++. So it's a totally different thing. And another part is in Python, and we will be doing everything in Python. And the states and all the matrices are stored in the form of NumPy arrays. Also, we are using OpenCV library to visualize stuff. And regarding the differential equations, we are using QP solvers, basically. It's
Uh,
yeah. Let me
Never
show
heard
you.
of the last one. What is that again?
Yeah. Let me show you. Hold on, just a sec. Just a second. Hold on. I'm going to show you. Okay, so now let me demonstrate the screen. Hope you can see it. Can you?
It's loading. Oh, yeah, I can see it now.
Okay, so there's the cart pole over here.
Okay.
And it's being driven so that it follows, its coordinate follows the sine trajectory. And
Okay.
the pole is not actuated, so it both follows the trajectory and stabilizes the pole at the same time.
Huh.
And this is done by a technique that is called model predictive control, MPC. It's reliant on predicting the behavior of the system up to a certain horizon, going with multiple discrete steps. And if I'm going to shut it down and check the code. So the simulation is kind of elaborate a bit. So there are 227 lines over here, but it all is written from scratch. So there's a simulation. Let me, my computer is dying. So sorry for the lags and the freezing.
Right.
But basically here, over here, you can see
Yeah.
very familiar things,
Uh-huh.
because those are the theta double dot and x double dot factored out from the same equations. So these equations allow us to get out the second derivatives of the coordinates, and using that we can first calculate them, and second propagate the system by the Euler integration. So we're numerically integrating the system and propagating it forward. And regarding solving certain things, there is
This is a lot to take in, but I'm really interested in like taking it step by step, like eventually. But
yeah, that's the plan basically. We'll have to assemble the group properly and start attending, doing home assignments, and that all of that thing, because there are a lot of people that are interested, but they do not visit each and every of our seminars. So it is difficult to catch up on the fly if you missed the last one. So
it's really
I'll have
hard
to yeah. So we'll have to organize that, and after that, we will happily proceed towards pendulums and stable equilibriums, certain approaches in describing and propagating the systems, and answering your question finally. So what do we use? We use this QP solvers. It's a library that's one of the ways of controlling the systems. It's not for integrating per se, but this thing is giving us optimal control up to a certain horizon with respect to the constraints by the metric that is given by a quadratic function. So let me just reframe it. I'm going to erase this. What is happening here is that we consider the evolution of our system up to a certain horizon. We're applying the control number 0, and we get into x1 starting from x0, and so on, and so on, and so on. Oh, you. And what we're doing is we're trying. Oh, let me see it. What we're doing is we're trying to minimize a cost function that goes as follows. It's a sum up to n minus 1 of the following thing. It's x transpose matrix q x sub I plus 1 transpose q x sub I plus 1, because it's from x1 through all of those up to x sub n.
I'm a bit
Plus,
lost. I'm a tad lost, but I think like once we really start working towards it, like step by step, I really appreciate the overview. I really do. But I'm a bit lost.
Okay. So
Yeah.
this is the state of the system, the initial state of the system.
Yeah.
And let us consider the evolution of the system after big N control inputs. The first control input, the second control input, and so on. It should not be that clear at this point. That's fine.
Yeah.
I'm just giving the idea of what's going on. So we are capable of changing these control inputs.
Okay.
And we're trying to find such a sequence of control inputs. So like push to the right, move front, then move to the left, and then move to the right again. This is the sequence of control inputs of the horizon 4, because there are 4 actions. And here it's the same, but the actions are just different. So the actions should be 3 newtons to the right, 1 newton to the left, and then 2 newtons to the right again. And it will be something like this motion. And we're trying to minimize with these controls such a functional u sub I transpose r u sub I. This is our cost function. It summarizes how much energy did we use and how far from the desired position have we been through our journey. This is what's happening.
I kind of get it.
Yeah, and the field of control and optimal control in particular deals with the problems that are kind of similar to this. So we're trying to get a sequence of controls that minimizes certain cost in some sense. And we'll cover the bloody details in their completeness.
I look forward to it. Thank you so much.
Yes, sure.
I'm excited to just take this step by step, and like, because this is completely new to me, but I really appreciate you explaining every little thing. And
sure, that I'm here to do exactly this. So
excited. Thank you.
Thanks.
Have a good day or evening. Bye-bye.
Yeah. Bye-bye.